Hello everyone, my name is Emma Chambers and I'm a postdoctoral researcher at the Dublin Institute for Advanced Studies. Today, I'd like to talk to you about imaging the temperature beneath Ireland and Britain using surface waves and joint geophysical petrological inversion. This research forms part of the DIG project, which I will describe in more details later. I should also add that it is funded by the Sustainable Energy Authority Ireland, Geological Survey Ireland and the Government of Ireland. And it's a collaboration with DIAS and also University College Cork. So why should we be interested in the temperature of Britain and in Ireland? Climate change is one of the critical challenges facing the planet. As this selection of newspaper headlines from both the UK and Ireland shows, renewable energy sources could be a way to mitigate climate change. And for Ireland, geothermal energy is being touted as a potential renewable clean heat source. Recent studies in Ireland have determined a higher than expected heat flow, suggesting geothermal could be a viable resource. And it should be noted that in Great Britain, geothermal energy has been used for greater than 35 years in Southampton, but as a small isolated project for a small scale heating system. But we should note that there is now in Great Britain, the recent United Downs project, where geothermal energy is being developed and the first steam has been produced at the Cornish power plant. Now, in Ireland, there are currently no power plants, but some small-scale heating system trials are currently underway at UCD, University College Dublin, making geothermal an underutilised resource at this present moment in time. Now, to see if geothermal energy is viable in Ireland, we first need to generate a more reliable model for the geothermal gradient across the area. Should be noted that this is specific to UK and Ireland. In Europe, these heating systems are already being developed. So, moving on, how can we map the geothermal gradient? Now, boreholes give us the most direct measurement of the geothermal gradient. The image in the centre shows current borehole heat flow measurements, which have been interpolated to produce the figure on the right. But as you can see, the points that we have are very unevenly distributed, with limited to no measurements in the south of the country. So the plot on the right gives us a good first estimate of heat flow, but is clear from the number of measurements that this is limited and over-interpolated. So other measurements and how we can constrain this come from indirect measurements. Seismic imaging can provide abundant complementary information to the thermal structure of the lithosphere, and we can use geophysical petrological inversion to extract this information from the seismic data, and by also incorporating other datasets, including topography, magnetotellurics, and also control source seismic models for the crust and lithosphere, along with additional components. So you may be asking why we need a lithospheric model and not just a crustal model if we're interested in geothermal. Now, the reason for this is surface heat flow on the Earth arises from two main sources, from the crust and also the mantle, which in continental settings, the mantle can count up for up to 50% of the heat production. Now, the geothermal gradient is the gradual change in temperature from Earth's surface to the core. In continental settings, the geothermal gradient is about 25 degrees Celsius per 1 kilometre of depth, as shown in the central figure. However, when we focus on Ireland, we can see that it actually has a higher than expected heat flow. And the geothermal gradient in Ireland is somewhere between 45 and 60 degrees Celsius per kilometre across the whole area, and in places sometimes higher than this. But often when we think of geothermal systems, we think of somewhere volcanic, similar to Iceland, as shown in the top image. However, geothermal heat can be accessed and used as a heat source in areas not associated with volcanism, and this is known as low enthalpy geothermal energy, which are most efficient for heating systems. In Ireland, 32% of Ireland's energy consumption is from heating, which are mainly produced from fossil fuels currently. But given that the recent studies show that the geothermal gradient can exceed 45 degrees Celsius per kilometre, this makes it a viable candidate for a low enthalpy geothermal system. And in Dublin, at 2.5 kilometres depth in a borehole, temperatures exceeded 60 degrees Celsius, sufficient for a low enthalpy geothermal system. The bottom right figure shows the Mallow warm springs in Ireland, and these are at a constant 19.5 degrees C. This might not seem very high, but this means that we have a higher than expected heat flow beneath this region. So this brings us onto the DIG project, which stands for De-risking Ireland's geothermal potential. The primary objective of the 48-month project is to de-risk borehole drilling costs to promote geothermal energy. We intend to do this by using multidisciplinary massive datasets and state-of-the-art techniques in order to generate a reliable geothermal resource map of Ireland. Our key objectives are to determine the regional geothermal gradient in Ireland using new and existing geophysical, geochemical, and petrophysical datasets. We also want to investigate the thermal chemical structure and the secondary fracture porosity within the Munster Basin, shown with the purple square on the figure on the left. And we're going to do that using wide-angle seismic, gravity, and geochemical data. Finally, we want to identify and assess the available low-enthalpy geothermal resources at a reservoir scale in the Munster Basin, such as the Mallow Warm Springs. And we're going to do this with joint interpretation of magnetotellurics and passive seismic modeling results, together with structural geology and hydrochemistry results. And so this is a very multidisciplinary project. But briefly, let's give you an overview of some of the geology. Now, Ireland itself formed as the result of the collision of the Laurentia and Avallonian terrains, which closed the Iapetus Ocean during the late Ordovician and Silurian times. When the ocean was closing, the oceanic lithosphere was subducted, subsequently forming the Caledonian orogenic belt in the late Silurian, early Devonian times. The Iapetus suture zone marks the collision zone between the two continental plates and extends approximately from the Shannon Estuary in the west of Ireland, across the Irish Midlands in central Ireland, and northeastwards towards the Scottish Highlands. We have granites in the northeast here, and also other intrusives marked in red in the west and east of Ireland. And previous work has included active source and MT profiles in Ireland, such as the Barnett profiles shown here and here in the southwest of Ireland, which also had magnetotelluric profiles along them. And they found that in the crustal thicknesses were about 29 to 32 kilometers thick. We have some active source profiles here which show this nicely. For my part of the DIG project, I aim to generate new surface wave dispersion maps of Ireland at a whole island scale, and also to produce crustal temperature models of Ireland with uncertainty, which is important because we're trying to de-risk borehole drilling costs here. So we need to know what the risk is associated with these. And this work builds up on the work of Raffaele Bonadio, and they've got a recent paper out in Geophysical Journal International, and they did the Rayleigh waves for this study. For this work, data has been collected from seismic stations throughout Ireland and Great Britain, as shown by the figure on the right. And you can see all these individual symbols are seismic stations present throughout Ireland and Britain. We use the two-station cross-correlation method and the automated multi-mode inversion method, otherwise known as AMI, for surface wave measurements, obtaining Rayleigh and Love waves, with the Rayleigh waves from the work of Bonadio at the top in grey, and the Love waves from this study at the base. Now, the reason that we want Rayleigh and Love is so that we can account for anisotropy. If I show you in the next two slides, the phase velocity maps, the interstation dispersion curves that I showed in the previous slide can be inverted to generate these phase velocity maps for Rayleigh, both Rayleigh and Love. We show that from these maps, Rayleigh waves have low velocities in much of Great Britain, but also some indications of slow velocities in Ireland. But we also need to do this for the Love waves. And if I flick to the Love wave component, you can see that the images are similar. We have some slow velocities in Great Britain and some still in Ireland, but they're not identical pictures. I'll flick back and forth a few times. Now, the reason that we've included the two types of surface waves is so that we can account for anisotropy and invert for isotropic shear velocity. Anisotropy can be caused by a wide variety of things, such as the alignment of minerals and crustal terrains, So we need to account for this to make sure that the velocities are related to variations in rock type or from temperature. We can also then invert the phase velocity maps, which currently are a function of period. So these are at select periods for different crustal and mantle depths. We can invert for depth so we get absolute depth trains. Now, currently, this has only been done for the Rayleigh wave component by Bonadio et al. And this was done using a purely seismic inversion. But by doing this for a shear velocity inversion, we get the depth at which these velocities are present. Now, these are absolutely fantastic inversions, but we want to add the Love waves to account for the anisotropy and invert for other properties, including density and composition. We don't want a purely seismic inversion. So this leads me on to how the shear velocity inversion can be enhanced. We're going to use a joint petrological geophysical inversion following the method of Falia et al. 2021. Now, the inversion integrates geophysical, geochemical, and petrological datasets in order to model regional crustal geotherms controlled by lithospheric structure. Rayleigh and Love dispersion curves are inverted along with the surface heat flow and isostatic elevation directly for temperature and composition in the crust and mantle, with density and shear velocity a useful additional product. We also need to input crustal thermophysical properties such as thermal conductivity and radiogenic heat production, which are from existing measurements in Ireland and borehole measurements. And we were requiring more data as part of the DIG project. In fact, at this moment in time, we have a team out in Mallow collecting magnetotelluric results for a more local scale study. Now, the output model is a series of 1D points across an area which can be gathered to generate a 3D model. If we watch this movie again, we can see that we could go anywhere in the world with this. Say we have a point in Ireland and we zoom in. We take this 1D column and we put in our initial phase velocity dispersion curves, selection of other data sets, and then we invert for shear velocity, temperature, and density. This 1D point in Ireland, just here, we could get a temperature profile like this. And from all these, we could put lots of other 1D columns all throughout Ireland, gather these together and make a 3D model, which is a combination of all these different slices. And this 3D model can show us the variations across Ireland and also Great Britain. So that's what we'll be doing in the future. So here we start to show you the preliminary results from the joint inversion. And this is for a 1D average profile for all of Ireland. Here are the dispersion curves for the average dispersion curves for first Rayleigh and also for Love. And you can see that we have a very small misfit function for both. Once we've done this inversion, we get outputs for temperature, density, shear velocity in blue, and also the AL203 content, which gives us an indication of variations in the lithospheric and sublithospheric mantle compositions. And you can see that at some of these boundaries, we can locate the Moho at about 32 kilometers depth, and a LAB at about a lithospheric sphere boundary at about 90 kilometers depth to 100 kilometers depth. So there's quite a lot of text here, but what we've shown here is that we've produced shear velocity models for Ireland and Great Britain from the Rayleigh and Love surface wave data sets. They've got high regional resolution and provide insight into the lithospheric structure, and isotropic average shear wave velocities can be related to the temperature and composition. We've also set up the inversion to be capable of incorporating those magnetotelluric data sets that I said are being collected, and also ambient noise data to get kind of the shallower structure in the uppermost crust. Now, the current phase and shear velocity models for Ireland and Great Britain by themselves provide enhanced resolution and insight into the lithospheric structure. But we aim to enhance this work by firstly making the joint petrological and geophysical inversion into a 3D map across all of Ireland and Britain, providing temperature, heat flow, and density information at unprecedented resolution. I should also note that this uses the software, the LitMod software developed by Javier Falia and in 2021 with the Winter Sea paper. So the goals in the future are also to add the MT data into the inversion to further constrain the temperature distribution and lithospheric structure, and also incorporate these ambient noise measurements. And it will then be used to determine areas of interest for further geothermal exploration, where we can then carry out additional MT and seismic surveys, which can be incorporated into the model, and find other areas that have a high potential for geothermal exploration, such as the Mallow Warm Springs. So to conclude, I hope I've convinced you that geothermal is not just for areas like Iceland, and that while we may only drill into the crust for geothermal applications, we need a full knowledge of the full lithospheric system to fully understand the geothermal systems. We've started joint petrological and geophysical inversions to determine shear velocity structure, temperature, composition, and density across Ireland and Britain. And these are going to be scaled to create a reliable 3D temperature and geothermal resource map of Ireland with uncertainty. So, should add that any updates to the DIG project will be posted to dig-geothermal.ie. So check that out. And also, thank you for listening. I'm happy to discuss the research further, so please send any messages that you have. Thank you.